Welcome back to statistics. Correlation, we've seen, is a measure of the strength of a linear association. The sign of the correlation coefficient tells you the direction of the association, and how close the correlation coefficient is to its extreme values of +1 or -1 is a measure of how strong the association is. We've also seen how the correlation coefficient plays into the formula for the slope of the least squares regression line. But there's yet another connection that correlation has to regression. It turns out the square of the correlation coefficient, r squared, is a measure of the fraction of so-called explained variation in a regression. One way to think of this is it's a measure of the goodness of fit of the regression line to the actual data. And so I wanted to take a few minutes and explain that idea to you in this short video. It all has to do with explaining and sort of apportioning the variation in the response variable in a regression. It turns out that there are two sources of variation in the response variable. The first is variation due to the linear trend itself. That is, even if the response data adhered perfectly to the trend line, it would still have variation simply by tracking along that trend line. We call this part of the variation the explained variation, or the variation due to the association. But there's a second part of the variation too, the variation due to the data's deviations from the trend line. This is called the residual variation, or the unexplained variation. And the total variation of the response data can be expressed as the sum of the explained variation and the residual variation. And the coefficient of determination measures the fraction of the total variation in the response variable that's due to the linear trend. In other words, the fraction of the explained variation as a part of the total variation. So I have some graphs here that illustrate this concept. In data set 1, you see a perfect positive linear association. And in data set 2, you see a weak positive linear association. We can compute regression lines for both those data sets, and there you see them. And if you think about the variation in the response variable, in the y variable, and you think about the graph number 1, there is going to be variation in the response variable, but it's all because the data are tracking along that trend line. And so in that graph, there's no residual variation because there are no residuals in data set 1. In data set 2, however, there's significant residual variation, right? In addition to the data sort of having that rising from left to right feel because it's tracking the trend line, there's also the separation, the scatter of the data about the trend line. And that's measured by the residuals, the vertical distances from the data points to the trend line that you see in red there. Now, if you look at the fraction of the total variation that's due to the variation associated with the trend line, for data set 1, that would be 100%, right? Because all the variation in y is associated with the data points, climbing along that trend line. Whereas for data set 2, the fraction of explained variation is going to be less than 1. Some of the variation in y is due to the data tracking the trend line, but not all of it. There's more variation in data set 2, and that's because we have residual variation. The data do not adhere perfectly to the trend line. And it turns out that the fraction of explained variation, that is, the variation in the response variable due to the linear association with the explanatory variable, is equal to the square of the correlation coefficient. So if you take the response variation due to the linear trend and divide it by the total response variation due to both the linear trend and the residuals, you get a value that's equal to r squared. So we can think of r squared as a measure of the goodness of fit of the regression line, as a measure of its predictive power. If r squared is perfectly equal to 1, then the fit is perfect. The data fit perfectly on a linear trend line. To the extent that the r squared comes off of that value of 1 and heads towards 0, the fit is getting less perfect. So again, if you look at the two data sets we've been looking at and you actually compute the correlation, for data set 1, of course, it's 1, and so r squared would be 1. So 100% of the variation in data set 1 is explained. It's due to the association of the data and the trend line. But in data set 2, the correlation is not 1. It's actually 0.679. And r squared is 0.461. And so what we can say is that 46.1% of the response variation in dataset 2 is due to the linear trend. The remaining 53.9% of the variation in the response variable in dataset 2 is due to the residuals, those red offsets you see of the data from the trend line. We consider that variation to be unexplained, right? It's not explained by the trend line because it's not associated with the trend line. So there is the idea of r squared, the coefficient of determination. R squared is universally used as a measure of the goodness of fit of your linear model, your linear regression. And so you'll see it reported by any decent statistical package. We'll have a little bit more to say about regression coming up. In the meantime, let me know if you have questions, and take care.